But there was no great particle physicist in Tokyo, so he studied the physics of solids instead. From Tokyo, Nambu moved in 1949 to take up a professorship at Osaka City University. 3 years later, he was invited to the Institute for Advanced Study in Princeton. He moved to the University of Chicago in 1954 and was appointed to a professorship there 4 years later. In 1956, he attended a seminar given by John Schrieffer on the new theory of superconductivity he had developed together with John Bardeen and Leon Cooper. This was an elegant application of quantum theory to explain why certain crystalline materials, when cooled below a critical temperature, lose all their electrical resistance. They become superconductors. Like charges repel each other. However, electrons in a superconductor experience a weak mutual attraction. What happens is that a free electron passing close to a positively charged ion in the crystal lattice exerts an attractive force which pulls the ion out of position slightly, distorting the lattice. The electron moves on, but the distorted lattice continues to vibrate back and forth. This vibration produces a slight excess positive charge, which attracts a second electron. The upshot of this interaction is that a pair of electrons, called a Cooper pair, each with opposite spin and momentum, move through the lattice cooperatively, their motion mediated or facilitated by the lattice vibrations. Recall that electrons are fermions and, as such, they are forbidden from occupying the same quantum state by Pauli's exclusion principle. In contrast, Cooper pairs behave like bosons, which are not so constrained. There is no restriction on the number of pairs that can occupy a quantum state, and at low temperatures they can condense, gathering in a single state which can build to macroscopic dimensions. The Cooper pairs in this state experience no resistance as they pass through the lattice, and the result is superconductivity. What worried Nambu was that the theory did not seem to respect the gauge invariance of the electromagnetic field. In other words, it did not seem to respect the conservation of electric charge. Nambu nagged away at this problem and was able to draw on his background in solid-state physics. He realized that the Bardeen-Cooper-Schrieffer BCS theory of superconductivity is an example of spontaneous symmetry breaking applied to the gauge field of electromagnetism. Examples of symmetry breaking are common. A pencil balanced on its tip is perfectly symmetrical, but very unstable. When it topples over, it does so in a specific, though apparently random, direction, and the symmetry is said to be spontaneously broken. Likewise, a marble balanced atop a sombrero is perfectly symmetrical, but unstable. The marble rolls down a specific, though apparently random, direction and comes to rest in the shallow brim of the hat. In truth, tiny fluctuations of the background environment are responsible for the pencil toppling over or the marble rolling down the hat. These tiny fluctuations form part of the background noise. Spontaneous symmetry breaking affects the lowest energy, so-called vacuum state of a system. Like any material, a superconductor could be expected to have a vacuum state in which all particles retain fixed positions in the lattice structure and its electrons remain motionless. However, the possibility of cooperative motions of Cooper pairs mediated by lattice vibrations results in a vacuum state that is lower in energy. In this case, the unitary group 1 gauge symmetry of electromagnetism is broken by the presence of another quantum field whose quanta are the Cooper pairs. The laws describing the dynamics of electrons in the material remain invariant under the local unitary group 1 gauge symmetry, but the vacuum state does not. Nambu realized that because the Cooper pairs exist in a state of lower energy, it is now necessary to input energy to break them apart. Free electrons created in this way would possess an additional energy equal to half the energy required to break the pairs apart. This additional energy would appear as extra mass. He was struck by the possibilities and summarized these some years later as follows. What would happen if a kind of superconducting material occupied all of the universe and we were living in it? Since we cannot observe the true vacuum, the lowest energy ground state of this medium would become the vacuum, in fact. Then even particles which were massless in the true vacuum would acquire mass in the real world. Break the symmetry, Nambu reasoned, and you get particles with mass. In 1961, Nambu and Italian physicist Giovanni Giornalasigno published a paper which outlined just such a mechanism.